Hey guys, and welcome back to another episode of Physics in 5. And as promised last week, I said I was going to either do Newtonian mechanics or generating electricity, and as you can see from behind me, we're doing generating electricity. There are many ways that this is done currently: renewable resources and fossil fuels and nuclear power, etc, etc. But there are really only 4 types of ways that electricity is actually generated, and it's just utilised in different ways. So we're going to be taking a look at the main way that electricity is generated, and then we'll go on to look at the other ones in later episodes. So yeah, let's get going. So the main way that electricity is generated, whether that be in a power station or in a wind turbine or using hydroelectric power, for example, or even nuclear power, is by utilising this thing called magnetic flux. And to utilise magnetic flux to generate an electric current, what we have to do is rotate a magnet inside a closed loop of conducting wire, such as copper wire, for example. Now, to do that, we have to figure out a way to generate a kinetic energy to begin with to turn a turbine. And the most common way of doing this is to heat up something and turn that into a kinetic energy, and turn that chemical energy into kinetic energy to turn the turbine, which is connected to the magnet, which rotates the magnet. If kinetic energy isn't an issue, such as in wind turbines or in hydroelectric power where the water and the wind are currently doing the motion, then you don't need to burn anything. And that's the main issue that power stations have, is that they have to burn something to generate enough thermal kinetic energy inside the water to generate steam to turn the turbine. So what is magnetic flux? Magnetic flux is a change in magnetic field over a particular area. As we can see here with a capital B vector, that is the magnetic field, and it's given as a function of distance and time, and it's multiplied by a surface area from which it cuts. It's integrated over this entire surface, and being as the surface can change with time, say the magnet rotating inside a conductor, it's given as a function of time, because the magnetic field is going to change with time. The larger the area of the object, the larger the flux. If you remember this drawing from last time, this is a rough drawing of a bar magnet indicating magnetic field lines. All magnets will emit field lines similar to the way electric field lines form, and these radiate outwards from the magnet in terms of strength of magnetic field, which is given by the B. And the B field also has a direction, and the direction is what governs the movement of the free electrons inside the conductor. Now, I'm aware that raises more questions than it answers. What is a free electron? Inside an insulator, all the atoms and electrons are tightly bound, so nothing wants to move. But inside a conductor, and by that I mean an electric conductor, there are free electrons which are free to move around anywhere inside the object, or even, with enough energy, escape the object. Now, a moving charge inside a conductor generates a current, so if you can get enough of these charges to move, you will generate current. The force that causes a charge to move is called the electromotive force, and here's where Faraday comes into it. Faraday's law says that the induced electromotive force in any closed circuit is equal to the negative of the time rate of change of the magnetic flux enclosed by the circuit. And yes, I had to read that. It's a bit of a mouthful, but what does it actually mean? So as we've already stated, this magnetic flux can change with time, provided the B field and the surface area of the object remain the same. The only thing that will change is time. How do you get magnetic flux to change with time? You rotate it so that it hits multiple different conductors, therefore it's not on the same conductor at the same time. Therefore, from the conductor's perspective, the magnetic flux it receives changes with time. Sometimes it will be present, sometimes it won't be. And while that's all well and good, you're not going to generate much of this electromotive force if you only have one single closed loop of conductor. So what Faraday's law states, electromotive force generated is also proportional to the number of turns on the coil, given by this symbol N. This is referred to as Faraday's law of induction. When the magnetic field changes, Faraday's law of induction says that an electromotive force will be generated to move the electrons. This in turn generates a current. Now, I had to look this bit up because I really didn't know myself, and it seems that there's not many answers in terms of this particular question. and that is exactly why does a changing magnetic field generate this electromotive force within the electrons. Honestly, I saw a few questions being asked in terms of scientific forums from December last year, and according to them, there's still no answer. So at least that's something to look forward to, is that we may finally know why this happens. So there you go guys, that's how to generate electricity using a kinetic energy source such as a turning turbine. And like I said in the video, there are many ways to generate that kinetic energy. Some of the ways are natural, such as wind or water moving past the turbine, but the majority of the time it involves heating something up and boiling water. If you liked the video, that's great, I hope you did, and you can go and check out more stuff like this at physicsexplained.co.uk. And if you did like it, why don't you hit that like button or hit that share button, because you never know, somebody else you know might also enjoy it. That's it from me, I will see you next week. Thank you for watching.